Okay, I think let's start, huh? More than half of the class is present now. We are total seven, so four are here. Okay. Previously, we are finished with this topic of time complexity, and we learned some rules here, rules for comparison, return, assignment, reading variables, and then rule for loops, and then rule for two nested loops or nested loops simply. And now we are uh, looking at an example of a binary search. And then here on in this example, we will calculate the time complexity, but first statement by statement complexity, which means line by line. We will calculate the line by line time complexity of this binary search. And whatever the rules we have learned before, we will apply those rules here. For example, here we have a method or a function for the binary search, and it is represented with the def. Def is for method. You can remove it. And then binary search is the name, and then parameters are some array and the element that you have to find in this array, which is called target. So, okay, this definition, it will take order of one time, constant time. And then we have a variable low is equal to 0. You are assigning some you already know the binary search from different courses, huh? How many you already have studied binary search? Raise your hands. You have studied binary search, huh? You know how it works. I'm asking because then I will not go into the detail of it. So So here we are setting two variables like low and high, which will work as the starting and ending index for the array. So low is equal to 0, which is the starting index of the array, and the high is equal to what? Length of the array. We are calculating, and low is equal to 0 is assignment. And for assignment, we have a constant complexity. So that's why order of 1. And this is also assignment without understanding. So I'm just saying length of the array. Okay, length of the array would be what, and then -1 high. So this is also assignment statement to order of 1 without understanding, just looking at the sentences, because our objective is to calculate the statement by statement time complexity. But you also have to, this is not only that, okay, this is assignment statement, so this is order of 1. Okay, here it is easy, but sometime you have to see that what is going on there, the execution. For example, here the loops, and in the loop, now if it is a loop, now according to the rule, you have to see that what is the block under this loop, what is the time complexity for it, and then you have to see how many times that loop is executing. That will become the complexity of this block. For example, if you remember this loop is executing n time, but there is the block is containing only one order of one statement, but this n time. So this one will execute n time. So this what? C out statement is order of 1, but the loop is executing what? N times. So then we are multiplying n multiplied by 1, and we are saying order of n linear complexity due to this law of for loop. This is the rule that we studied previously. And for two-dimensional, this is n, and this loop is going n by m, and this is one time. So n multiplied by m multiplied by 1. So you have to multiply when you have a loop. And here, I don't know. This is related to previous lecture. You can watch the lecture on a YouTube. Okay. These are simple variables. These are the simple variables. N is the last. These nm that you used here, in these loops, okay? Yeah, this loop is going n time, this loop is going m times. And this is already previously I recorded and I uploaded, okay? And in each lecture, you are waking up and you are saying, okay, what is this one? Huh? You were there in the previous lecture or not? Okay. While low less than equal to high. So initially low is 0, high can be, if the length of the array is 5, then array can be 5 and low can be 0. And this 0 less than equal to high, okay, but we don't know how many times this loop will go. For the first 0 less than equal to 5, yes, it is okay. Condition true, and the block will execute. Huh? And the block is starting from here and going up to here. All these statements are under this loop. So, but at this point, we don't know how much time this loop is going on. So we have to understand this block first. That's why I was saying that it is not necessary, okay, this is arithmetic statement, so order of one. No, you have to, this is a loop first. And loop, how many time it execute, you have to understand. And for its understanding, here in the for loop, all the things are given here. So that's why I can identify from here that it is executing n time, huh? And it is executing m time from here. But here it is a while loop. How many time it is executing? I have to see this block, because then here in this block we will handle low and high. And here we are doing what? Low plus high minus low divided by 2. In some binary search algorithm, you are only doing what? Low plus high, and you don't have any low, huh? And then divide by 2. That is also okay. But in that, uh, sometime you will not get whole numbers or something like that. You are dealing with the integers, sometime answers can be wrong. Anyhow, that statement is also okay, and this statement is also okay. So if I will, it's up to you. You can go with low plus high divided by 2, or like this. So you are adding starting index, ending index, adding them, and you are dividing it with 2. So if starting is 0, if it is 0, and if it is length of array is 5, 5 minus 1 is 4, for example, if the total size of the array is 5, then here, so then length of array is 5 minus 1, it is 4, 0 to 4. So 0 plus 4, 0 plus 4, 4, 4 divided by 2, and then you will have, in the for the mid you have to. Hmm? You know, I will start after Adana. So, so 0 plus 4, 4 divided by 2, you have 2 here. And then you are checking that array into mid, which means if you have some array like that, 5 elements, then you are checking, then 0, 1, 2, this is the mid index. So array into mid, you are checking this element with the target, the element that you want to find. If it is equal, then you are returning that this is the location, this is the mid location of that element. If array into mid, if this number is less than target, if it is less than target, array into mid means this element is less than this target, then you are doing what? Then low is equal to mid plus 1. If this element is, if your target is higher than this, which means array into mid less than target, this element is less than target, which means target is higher. It means it is on that side. So then you are doing what? This mid plus 1, this index, you are making it low, and the high will remain as it is, huh? And in the else portion, if this is not the case, then opposite. Then it means your element is on that side. Then you have to do what? Mid minus 1. You have to move this to here, mid minus 1. And that will become the high. Your low will be as it is. You already know that. So now after having this, so this block is doing what? It is dividing your array into half. Okay. This you know, huh? How it will work, we are not concerned. But in the first step, it is dividing your array to half like that by finding the mid position and then adjusting the low and high ends in each step. Okay, if in the next step your element is here, then your low is here, your high is here, and then it will divide again. On each step, it is dividing the array into half. When so this loop is executing what? If it is dividing your array into half, which means it is initially your problem have, for example, 5 elements. Then in the second step, you have only 2 or 3 elements remained. Then in the next step, you have 1 or 2. So in just maximum 3 steps, you will find your solution. Huh? So you are not doing comparison with all the elements in the binary search, which is five comparison. No, 5 and 6 for the linear search. And if it is linear, then it would be 6 comparison. But you are just doing 3 comparisons maximum, and then you are going out. So this loop and this block is what? This is an assignment statement. You are calculating mid order of 1. This is comparative statement. According to rules, it is order of 1. Return statement, according to rules, order of 1. Comparative statement, conditional statement, order of 1. Assignment statement, order of 1. Else, order of 1. This is order of 1. But this loop, which is containing this comparative statement, this is order of 1, but how much time this is executing? If low is 0 and high is 5, which is n, when your algorithm on each, this algorithm is dividing your problem on each step, you're dividing your problem into half. When you have this property, then the complexity for that thing would be log of n. If you will take the log of n 5 base 2, you will get maybe 3 answer. Okay, that is showing this maximum number of comparison. 2.5 or 3, you will get that. So what this log of n means? It means if n is 5, which is the number of elements, you will take the log, you will get 2.5 or 3 maybe, which is, so that's why we are representing that how many times this loop will execute. We are saying in mathematics way, log of n times. So this loop will execute how many times? Log of n times. Now, if you will sum up all these, if you will put plus here, for this loop, log of n times, okay, for this order of one, 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 when you will add them up, it is 1, 2, 3, 4, 5, 6, 7, 8. 8 is again constant, huh? 1 is constant, 8 is again constant. And then how many times? Log of n times. So for this, you are getting log of n. And then plus this last one. You are ignoring all these. You are writing this in a line. Order of 1 plus order of 1 plus order of 1 plus log of n plus order of 1. And then you ignoring all constants. And then the remaining would be what? Log of n. And this is how you can finally write that the complexity for this is log of n. Complexity for the binary search is big O of n. Order of big O of log of n.
So, previous slide, why you say local and why you say only on and only in?
Because loop is not executing n times. How many times this loop is executing? I explained this. I explained this. How many times this loop is executing? N means what? If the size of the array is 5, then n means what? 5. 5 or not? Here n means 5. N is the size of your input in algorithms. Whatever algorithms will come in futures, n is always representing the size of your input. Okay? And here input is array. And if the size of the array is n, and if I am giving n is equal to 5, then the array is containing what? 5 elements. And if n is 5, then I am saying log 5. Then I am saying log 5. And you are saying why I am not saying 5 only and why I am saying log 5. Huh? This is your question. And then I am asking how many times this loop will execute if the size of the array is 5. How many times this will execute? How? 5. It will not execute 5 times. I was explaining this. I was explaining this. I don't know where you were at that time. I was telling you that this block is doing what? It is dividing your problem into half, not into two, into half each time. It is reducing the size of your input. On the first iteration, low 0 is equal to 4. Okay, it is executing for the first time. Then it is dividing this mid. And then it is reducing the size from 5 to 2 or 3, maximum. Yeah. Remaining elements would be 2 or 3. First 5 elements, then remaining elements would be 2 or 3. This algorithm is going to consider. In the next step, it is only 1 or 2. So how many iterations? Only 3, not 5. How many times this loop will execute? Only 3, not 5. So what this is doing, it is reducing my problem into half. And when in some, so that's why individually this statement is order of n, individually. Order of 1, 1, 1, 1, 1, 1, individually. But block wise, what is the complexity for this? Block wise, reducing into half. When some statement or block is reducing your problem into half, then the probability would, complexity, sorry. Sometime in the other course, I'm using probability and probability here. So complexity, then you can represent the complexity with the, when an algorithm has this property, reducing into half, then you can represent the complexity of that block with log of n. Why? Because mathematically it is correct. If you will calculate log of 5, you will get 3. And this is what I want to say.
Instead block to take a long time, it will reduce. So you don't come inside the block, but the block actually the execution is going to be sure.
If you are saying that this while loop is going to be short, on each step, that's okay. Yeah, that's okay. So, so actually your input is 5, 5 elements, and the maximum number of comparison is 5 or 6 to find the number in this array, maximum number. But this loop with low and high, it is reducing your problem into half here in this block. This loop will execute if low is equal to 4 or 0 and it is 4, it is executable first and then it will find 2. Now, according to these conditions, it will adjust low and high, and then the size is reduced to half. In the next iteration, it will reduce to half. So the maximum iterations for this loop, if it is 0 to 4, it can be 2 or 3. I am also saying 3 on a safe side, okay? For the safe side. So for the safe side. So for 5 elements, this loop is executing 2 or maximum 3 times. And when in your algorithm, when some block is reducing the operations into half, then this is the probability that you can represent with log of n. N is the total number of elements in your input.
You don't consider the line inside the block. You don't count.
I counted them, which it is a constant. It's constant, and finally you will ignore the constants, okay? And then finally, you will ignore the lower terms and you will keep only the higher term. And these are the lower terms, 0, 1, and this 0, 1. And finally, higher term is only the log of n. That will become the complexity of your algorithm. The reasons are mentioned here in this next slide. While loop is doing what? It is reducing the search space by half in each iteration. Okay. So this reduction, this logarithmic reduction, then the worst case means big O, then the worst case time complexity, which means maximum number of comparisons for this would be order of log of n. You will ignore the constants, where n is what? Number of elements in the array. N is always number of elements in your input. What would be the best case scenario? Okay, worst case is big O, but what would be the omega? If best case is that when this iteration is coming for the first time, 0 less than 4, and you will find the mid, and array into mid will become, this condition will true, you will become true, you will return mid and out. You will make only one comparison. That would be the best case, If you will find your target at the first comparison, that would be the best case. And here you are doing what? You are executing this loop only one time. And this is also order of 1, order of 1, order of 1. Now this is also order of 1. So the best case, so for best case scenario, or you can say, here I must have to write omega, not big O. Okay. So omega of 1, which will represent the best case, And the reason is mentioned here, that you will find your target in the middle. I will upload, this is your assignment, and I will also, assignment part A. So then assignment number 1, part B will also come. When it will complete all the part, when all parts will be completed, then I will upload this assignment on the Blackboard, and then you have to submit it within the deadline. What it is saying calculate the statement by statement complexity of this algorithm, which is Euclidean algorithm, and then calculate the total time. First, give me statement by statement and then sum them up. Ignore the lower terms, take only the higher one, and that would be your total time complexity. Okay. By the way, here's it is already given. Huh? Some statement it is given, it is this is not given, this is not given. You have to write it by yourself, and then you have to write it in summation form, and then you say by ignoring lower terms and taking only the higher terms, what would be the final? Final would be this one, order of log of. What is this? You have to see, huh? Now moving on to space complexity. Understood this time complexity. Now you understood how we can calculate the time complexity of an algorithm. Okay, this is just one example. Huh? Space complexity. By the way, calculation of space complexity is also similar to time complexity, but some rules are different. You will see. So space complexity means we have to count the memory that algorithm is taking. Huh? So what amount of memory algorithm is taking, we have to count that, and that is called space complexity. How we can compute that? Number one, memory, your how much memory your algorithm is taking. Rule number one. If we have an array of size n in our algorithm, then it means our algorithm is taking order of n space. Okay. Memory. Okay. If our algorithm has two-dimensional array of size n cross n, then it means that it is taking order of n square space. It is like two nested loops. Huh? It is like single loop, and it is like two nested loop. But here we are talking about memory. So if we have two-dimensional array, then this is n cross n, and then we can represent order of n square, and it we can represent order of n. Now, rule number three, which is actually crucial. Huh? If we have a recursive algorithm, then in that algorithm we will have some recursive statement, which means the function will call itself. Huh? That is called recursion. Huh? And when we have recursion in our algorithm, then we have to see how much time that recursion is going on. And if that recursion is going on n times, and then how we have to see what is, for example, here the function is int add and the parameter is n, then the bracket is starting, bracket is ending, and here this is the body of this function. Huh? We have to calculate the complexity of this body like a block of the loop, and then we have to say how much time this, and here n is equal to 0, return mean go out and return this value, and then return n plus add. We are calling this function again. This is what recursion is called. Huh? This is recursive call, calling itself. So you have to calculate how much time this recursion is going on, because in computer programming languages, when you are using recursion in your algorithms, then a stack will be created. When your program will run and your program has that recursion inside, then a stack will be created. And then on each call, the values will be pushed into the stack. And when all the recursion will end and the base case will execute, that will return some value, and then pop up, all values will happen. And finally, the stack will be empty. And that stack, you know that it is a kind of a data, it is a data structure that you studied, and it means it will take memory. Huh? So for example, here, if you are taking n is equal to 4, to understand it further, let's see. If n is equal to 4, then the first call is add is equal to 4. And then, okay, 4 less than or equal to 0, false. And then you will come here, return 4 plus add into 4 minus 1, 3. So you are calling add with 3. Yeah? So you will call add. And when you are calling add 3, 3 less than 0, and then again you will reach here, and 3 minus 1, you will call add with 2. Then you will call add with 1. And finally, you will call add with 0. When 0 will come, 0, 1 less than, no. 0 less than or equal to 0, yes, condition true, 0 equal to true. And then return true. This, when you are calling, you are pushing these values in the stack. And when the base case is executed, return 0, 0 equal to 0. Okay, this will give you 0. This value will go back to the previous call, to the previous call, to the previous call, to the previous call. And the values will be popped up from the stack. How much time these calls are going on? If your n is 4, then I can say it is executing n times, huh? It is calling how many times? N times. N is the size of your input or whatever, huh? This is the input to this function, n. And if it is 4, then the number of calls would be what? 4 and 1 extra, like loops. So, and here, this statement is comparative, order of 1. This is return, order of 1. This is also addition, order of 1. But this is main thing here, huh? Only. So the block has order of 1. But I have to identify that how many times this is executing, repeating, or calling. Then this is saying that if n is equal to 4, then it is n time. That's why the complexity of this this module or method is order of n. Understood? Understood? Ghazi? Okay. This is due to recursion. But sometime in the code, you are calling some function. But when you are calling some function, it doesn't mean that it is using stack. Huh? Only for recursion, your compilers are using stack. But if it is a simple call to function, then no stack, okay? It is only one time. It is happening and just. So then what? For example, here in this example, we are saying that if you are calling functions or calling method, then it doesn't mean that you will consume stack memory always. For example, here in this code, int add sequence, int n is the parameter, sum 0, and then we have a loop I is equal to 0, I less than, which is executing n times, okay? I have mentioned it n time. And this statement, int sum is equal to 0, order of 1. This definition is also order of 1, but I didn't mention, huh? Because there's no need to mention it. It is always order of 1, huh? Sum plus is equal to pair sum, and then we are calling some function which is written here, pair sum with these parameters. So this is also assignment statement, so order of 1. And then loop is finished, return, we are returning sum, which is that variable. Okay, this method is finished. And then int pair sum, we are passing two variables, x and y, which from here. And then we are adding them and returning them. So if you are passing two numbers I and I plus from here, and that will go here in the x and y, which will be added, and after addition, value is returned here. And that returned, you will have value here. Huh? After addition, if it is 5, then you will have 5 here. That will be added here. So that method, that function was initiated and then finished, huh? Because you are returning. You are going out. The scope of the method is finished. While here, the scope after calling add into a 4, it is not completed yet. It is still in process, huh? And then you called further add 3. It is in process. It is not finished yet. Due to this, it is still in the memory. But here, you call this, it is process has been done, and you are returning, it is finished. So order of 1 time only. It is not in process. If it is not, and when you are going for I is equal to, it is I for I is equal to 0. When it is I is equal to 1, you are calling it again. You are calling it again, adding, returning, and finished. Order of 1 again. Huh? So calling this function again and again, it is always order of 1. It is always order of 1 for this statement. So that's why I am also saying order of 1 here. But this loop is executing order of n times. Huh? So for this method, complexity is order of 1 for the complete method. But for this method, 1 order of 1 are ignoring lower terms, your final complexity for this method is what? Order of 1 or order of n? Asking you. The complexity for this method, the complexity for this method, total complexity for this pair sum is always order of 1. But my question is, what is the complexity for this method add sequence? Order of n. Why? What is the reason that it is order of n? What is the reason that order of n is the complexity of this add sequence? What is the reason? Due to this loop. This loop is executing n time. And sorry, we are we are not calculating runtime, okay? We are calculating space, okay? So then we don't have to consider this loop, okay? Okay. If there would be an array, then we can say, but here we don't have an array. Okay. Here we don't have an array. So, okay, for space complexity, loop doesn't matter. One-dimensional array, two-dimensional array, recursive calls, iteration matters. And here we are iterating, but one each time. Uh, for this recursion, we are using stack. So that's why we are saying order of n. We are not saying that it is iterating 1, 2, 3. No. We are using stack n times. That why. And stack is a data structure like array. That's why we are saying array. Okay. Sorry, here order of n was written. That is wrong. Okay. This is not order of n. It is not running time. We are talking about space. For space, loop, we will not consider loop, okay? So then what would be the space complexity for this? Order of 1, 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 finally order of 1. Okay? Because we don't have an array in it. And here we are calling function that is calling, adding, and returning and going out of that function. So push and pop together, huh? You are using stack. You are pushing, but you are popping again. So order of 1. You are if it would be like that, push, and then you are calling another function, then again push, and then pop together, then it would be that criteria of regression. But this is not happening here, huh? So this is the code. So that's why I mentioned here question mark here. Why I mentioned? Because I was thinking to ask you what is the complexity over here, but I identified that here it is something mistake I made it did it here. I was calculating running time. No, running time, no, space. For space, it is not order of 1, it is order of 1. And then the final complexity for this method is also order of 1. And for the total, order of 1. This is what it is mentioned. I will also correct this, huh? Order of n calls to pair sum, okay, but do not exist simultaneously. Stack due to yeah, yeah. I will correct these lines, okay. Uh, Now recursive binary search. Previous binary search that you have seen was iterative. Iterative means containing loops, huh? And no recursive calls. But this binary search that you will see here, it is recursive. You are calling the function itself. Function is calling itself. For example, here the name of this function is recursive binary search. We are passing array, the target element that we have to find in it, the low starting index and the higher index, ending index. And this binary search is also behave like the previous binary search, but in a recursive way. And here first we are checking if your low is 0 and if your high is 4 for a array with 5 elements. Huh? And for the binary search, array should be sorted. Huh? Array would be sorted. This is the condition. So, and here 0 greater than, is 0 greater than 4? No, condition false. Then you will come here and low is equal to high minus low divided by 2. You can calculate it like that, or you can do low plus high divided by 2. No issue. And then you have the mid position, and here you are checking if mid is equal to target, you are returning that this is the location of the mid. If it is greater, if your mid is greater than target, mid is greater than target, if this is the mid, huh? And we are saying this mid is greater than the target, then it means our target is on this side, huh? It means our target is on this side. And then we have to do what? We are calling this recursive binary search again with array, with target, low, and we are reducing this mid minus 1. We are moving. We are not altering low, but mid minus 1. And if this condition is also false, then the last condition is what? We are moving in that direction, and that is array, target, mid plus 1. We are increasing mid plus 1 and the high. It is similar to that, but we are calling function. Function is calling itself. We are not using if conditions. Huh? We have used only if conditions. We are calling. We are not changing. We are changing within the recursive call. Function is calling itself. And we know that if this condition is true, this will execute. If this condition will true, this will execute. If this condition will become true, then this will execute. This recursive binary. Now, space complexity. We have to calculate space complexity, not time complexity. Okay. Single loop, double loop. And there are two kinds of space complexities. One other thing. I can say here, the complexity that you are calculating here, normally if in your algorithm there is a recursion, then the recursion lies in the category of auxiliary complexity. What is auxiliary complexity? The space that algorithm is using at the runtime, or the space your program is using at the runtime. I'm saying program for your better understanding. When the program will run, what space that program will use, because at that time recursion will execute. Huh? If you are not running, then we are not using space. Huh? When your program is running, at that time your recursion will execute and it will create the stack and use that. So that is at the runtime, not at the compile time. Okay. But on the other hand, there are some memories which are allocated at compile time. And those space complexities, you can call them physical space complexities, okay? Or you can call them an initial space complexity, or simply space complexity. And if I say auxiliary space complexity, then it means what would be the complexity this algorithm is taking at runtime. And you don't have to discuss real space which that algorithm is using. For example, one-dimensional array, two-dimensional array that algorithm is using. If I'm asking auxiliary space complexity, then you don't have to consider one-dimensional array, two-dimensional array. That is already defined in the algorithm. Okay. But if there is a recursion, you have to consider only that. And then you have to calculate the answer for that, and that would be your auxiliary space complexity. You have to take these concepts correctly and compulsory, because these concepts will come again and again in the next lectures. So you must have this ability to differentiate between the auxiliary space complexity and the normal space complexity. Normal space complexity is with the normal data structures. Recursion is not included in it. But if recursion, that comes in the auxiliary space. Okay. Now, I am writing it here. So this statement is written here. Definition recursive binary array target. So these parameters will take constant amount of time, order of 1. And this definition also will take order of 1. For the first execution, for the first call, it will take order of 1. When it will find recursion, then it will behave differently. Then, okay. And then this is that statement, low greater than high. This conditional statement, order of 1, constant. Return -1, order of 1. I am writing it constant, okay? And similarly, mid, low, this is constant. And here we don't have any loop. Okay. Again, I normally go into running time. We are not in running time, okay? We are in space. So for space, we have to consider the arrays or the recursive. In this binary search, we have this array. We are using this array. And whatever the size of the array is, so order of n is due to this array. And then, and here, but this low and high and this recursive binary search, this algorithm is reducing the size of the array each time into half. So this is one thing. Okay, this is each time into half. But here we have recursion. When you have that recursion in algorithm, you have to focus more on recursion. And this recursion, in each iteration, the problem will be divided into half due to this mid that we are calculating. And how much time it will execute? If the size of the array of the problem is 5, then again, it will execute log of n times, no worry. Then for 5, it will do what? How many operations? 3, 2 or 3. Same way. But here recursive calls are 3 recursive calls, okay? It will be 3 recursive calls. This recursion is behaving exactly like loops, but using stack. Understood? So for mid, low, high, okay, this will take constant. Array, comparative statement, constant. Return, constant. Else, this statement, constant. Then return recursive binary search, this statement. I am saying this statement. This statement and this statement. These are the recursive statements. And here I am saying about this is a recursive statements. This is a what? Recursive. When you are calling it, the name is same. The name is same. And the compiler will know that. Compiler already know. When you compile it, it knows that recursive call is there. But the stack would not be created, okay? When you will run it, at that time stack will be created, So now, when you are calling it again, now stack will be created. And when you are calling, you are returning from it only here or maybe here and not anywhere else. When the element is found or when your boundary is crossed from the last element of the array. Okay. Then this recursive binary search, then your stack is initiated with the first call. And that first call is pushed onto the stack. And then second call. For 5 elements, 3 times this will execute, either with that, either with that. So 3 times. So either with this or either with this call. And these two For 5 elements, these two collectively will execute maybe 3 times collectively. Maybe one time this, one time this, one time maybe this, then total 3 times. And then on there would be only one stack, okay? For this and this, only one stack because it is recursive. So 3 values would be pushed on the stack, and those 3 values will be popped when you will reach on the base case. When this base case or when this will happen. Then you are returning the value from, and then push will become pop, huh? So for this else, it is constant, but for these things, so 5 is the size of the array, which is reducing into half, which is 2 or 3 due to these recursive calls. Then auxiliary space complexity of this algorithm is what? Hmm? How much time? How much time? I am saying that the total size of this problem is n, which is the number of elements in the array. Huh? And array will take space. Huh? And so worst case time complexity of this algorithm is what? Order of n. Worst case, worst case. Worst case complexity of this algorithm without recursion is what? Order of n. But you know that due to these recursions, n is reduced to half. The problem is reduced to half. When the problem is reducing to half, how we are representing it in mathematics? Log n. Okay. These representation rules are same for the space and time. Okay. Log n. So here the auxiliary space complexity for this algorithm is what? Log n. Okay. Log n. This reason is mentioned here. Search space is halved in each step. Maximum recursive calls are proportional to what? Log n. If n is 5, then the maximum recursive calls would be what? Log n, which means 3. 2 or 3, huh? So the space complexity for this algorithm is order of log of n. And this is auxiliary space complexity. Okay. Due to what? Due to stack that we are using due to recursion. Understood? Okay. This is assignment number 1, part B. And what you have to do, algorithm for finding the least common multiple LCM for two numbers A and B. That is written here. And we normally use this. So this function LCM is given there for finding the LCM of two numbers. And here we are calling GCD, which is given here. And I'm in this I am asking calculate the statement by statement space complexity of this algorithm for finding the LCM first, then conclude the total space complexity. First, space by space. What is this? What is this? What is this? This space is taking order of 1 space, okay, due to variables, okay. If your variables also take space, huh? And they variables normally takes too much tiny memory, huh? Little memory. So that's why it is like constant, okay. So this is constant, this is constant, even print statement space complexity constant, okay. So these are ignorable values. So it's constant. So you can write them order of one like that until you have a array initialized, two-dimensional array initialized, or recursive calls. Here you have to think differently. These are the rules now you learned, huh? How can we optimize the complexity? What are the different options if we have to optimize these complexities? We have studied two complexity, space and time. For any algorithm, we have two complexities, space and time. There are others you will study in AI, huh? But here we are talking about only two, space and time. How, what you will do, and if you will do that, then that should be considered as optimization of that algorithm. What are those options? Number one, if you will reduce the time of the algorithm, running time of the algorithm, and when you are reducing, the space of the algorithm is increased. I don't want to increase the space, but if increased, but time is decreased, that is also an option for optimization of the complexity. That is also good, okay? At least you reduce the time of the algorithm, huh? Space is increased, okay, no issue. But you reduce the time, huh? The other option is you increased the time, but you reduce the space of the algorithm. That is also a good option. That is also a good option and considered as a optimization option for the complexity, which you can, if you will do this with some algorithm, then you can publish that as an article. That would be your research work. And the next is you can reduce both time and space. If you will do this, this is the most perfect option in all. You are not leaving any option loose. You are not leaving any loose option. Huh? So you are reducing both time and space. So these are the optimization complexity options. Now, from this topic to onward, we will say what are the different. For example, log of n is one way to represent complexity, and this is called logarithmic complexity. The title for this log of n is what? In mathematics, the name for this log of n is what? Logarithmic complexity. And now we will see different types of complexities. The names, huh? For example, first one is constant complexity. What is constant complexity? Order of one. We normally write order of one. Huh? In the previous practice, when we write order of one, what is the name for it? It is called constant complexity. That is the reason that you saw that here I was using constant. Huh? I can write order of one here, but I was saying constant. So now the name of this complexity is constant complexity. 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 Negligible execution time of an algorithm. That time which you can ignore, okay? Which you can ignore. Negligible means that a time of the algorithm which you can ignore for finding the final solution. And and which you can ignore, that is called constant complexity. For example, if you will take n is equal to 101 here, for this, what this algorithm is doing, it is calculating even and odd number, okay? So this n is 101, 101 remainder 2, the remainder will come here, and then you are checking if that remainder is 0, print even, else odd. Now, mathematical types of complexity. Here, when I say constant, here, now we are again going towards the concept of running time, okay? Normally in our practice, we don't calculate space complexity because now space is not an issue anymore. Space is cheap and available too much. Running time is major thing, huh? So most of the time, whatever you will see, mostly the calculation is about running time. And here we will again, we can represent constant complexity or whatever for the space and time both, okay? Whatever the notations we are going to learn here, these can be used for space complexity and also for the running time. Okay, now this is order of one, this is order of one, this is order of one, print statement order of one, order of one, order of one. So this algorithm do not have any loops or anything. I am considering running time, huh? So then order of one, order of one, order of one, if you will sum up, it will be order of maybe seven, but seven is again a constant, huh? So then this method contains constant complexity. In graphs, normally constant complexity means if you are here, complexity will go like that, constant, huh? On positive and negative points, it will go like that, constant. Hmm? This is graphical representation, nothing else. Number two, logarithmic complexity, which is log of n. You already know that. When you will write something into the form of log of n, that is, you are representing that complexity, and that is called logarithmic complexity. And when it will happen? When reducing the size n of the problem, when you are reducing. And I have mentioned here, mostly, usually, into half. It can be into 1/3, then you have to write n by 3. And here it is n by 2 actually, n by 2. But log will give you the right answer. So that's why. If you will divide 5 divided by 2, you will get what? Maybe 2.5. So that is log of n is like n by 2. Okay. Sometime you are reducing the problem like n by 3, n by 4. Then it is not log of n, huh? Then you have to write that mathematical formula. But here I am saying logarithmic complexity when you are using log. What it means when you are reducing the size of your problem, most of the time, when usually half, then that algorithm is imposing a complexity of order of log of n. I'm asking, here I'm giving you the definition. What is logarithmic complexity? Then you have to write what? When you are reducing the size of your problem into half, then the complexity of that algorithm is called logarithmic complexity. Okay. For this binary search again, if array is this, x is 10 element that you have to find, and r is equal to length of array minus 1 and r. And we already know from the previous examples that binary search has the complexity what? Log of n. We have seen that previously, huh? If I go quickly, okay, this is comparative order of 1. Assignment, order of 1, order of 1, order of 1, order of 1. Recursive call. Recursive call, okay. Order of 1. Recursive call, okay. Order of 1. So due to this recursive call, problem is divided into half. We know that, huh? Because it is binary search. And then I can represent it in 1. I can ignore all order of 1s. And finally, I will have what? Order of log of n. And how log of n will go graphically? For example, it's starting from here, and then it will raise a little bit, and then it will go like that. Okay, it is starting from here, from point below 0, huh? A little bit higher, and then it will go like that. And there is no anything on the negative side. What is linear complexity? Linear. There is a algorithm called a linear search. Linear mean whatever the size of the input is, if you have that complexity, if the input size is n, and you also have the maximum number of operations also n, then you can represent the complexity into the form of order of n. This is what called a linear, huh? Linear, straight and simple, huh? Straight and simple. When the number of operations are equal to the size of the input, okay? This is the definition. When the number of operations in an algorithm is equal to the size of the input, then that algorithm will have linear complexity, order of n. And how we can represent it? We can represent it like order of n. And for this short algorithm, if array is this is the element that you have to find. And the length of array, what if here the length of array is 5? So 5 minus 1, 4. So in the R you will have 4. And if you will do that, okay, order of 1, and for I in range length of array, this loop is executing n times. Huh? Length of array. Length of array is what? Length of array is 5. And range 5. So it will start from 0, 1, 2, 3, 4, but not 5. Last 5 will not considered, huh? This is a Python syntax, so that's why, huh? So I represented the Python code as a pseudo code for you because I removed other stuff, main, program, array, or what. I am representing it like that. I have shortened your algorithm because that is not the part of the algorithm, the other statements. Okay, and if this is order of one, this is order of one, this is order of one, but this block, which is this block is order of one, but it is executing n times. And due to this loop, I can say the complexity of this algorithm is now order of n. Hmm? Because this block is executing n time. I am talking about running time, not space complexity. And the linear complexity will go like that, straight, positive, or if downward, like that, in a diagonal. Quadratic complexity. You know the quadratic equation. X square something, x square plus maybe a square plus b square plus maybe b square minus 4ac divided by 2ab. I don't know. Something like that, huh? Quadratic equation. B square minus a plus minus b square minus 4ac under root divided by something like. So why we are calling that quadratic? Why we were calling that quadratic? Because uh, now I'm an old man, so that's why that quadratic equation we studied in our BS, huh? Or maybe in intermediate class. So, and after that, so now my memory capabilities are not at that your level, huh? So anyhow, so why we were calling that quadratic? Because it was square, okay? Due to the square was there. So quadratic complexity, how we can represent quadratic complexity? We can represent quadratic complexities in mathematics by using this order of n square. Order of n square. When this is order of n square, the name for it is quadratic complexity, theoretical name. What would be the situation that we have this quadratic complexity? When operation with constant amount of time appears under a nested loop, the easiest understanding is if you have nested loop and each loop is executing n times in some algorithm, then you can think first thing in your mind that here that block is order of n square, okay? The other statements are doing what? But that block is what? Order of n. And if other blocks are order of one, then the complexity of the algorithm would be what? Order of n square. If you have nested loops and each loop is executing n times, each loop is executing n times, then n multiplied by n, it will become n square, huh? And if in the algorithm there are some other statement, but if those statements are order of n, then you can ignore them, and then the complexity of this algorithm would be order of n due to these nested loops. This is the easiest identification if these nested loops are existing there. If three nested loops running n times, then n cube. 4 and 4. Okay, this is the logic. For example, here, if array is this, x is this, and this is the method check pair, this array is going into it, and this -2 is also going into it, and then this is the loop for I in range, size -1. Size is what? Length of the array. Length of the array is what? 5 here. So size is 5. So 5 minus 1. 5 minus 1 is 4. And then 0 to 4, almost 3 to 4 times. Huh? If the total size is n and loop is executing n minus 1 or n minus 2, that is also like n time, okay? Because this is theoretical calculation that you are taking here. And if some 1 or 2 points is plus or minus, no issue in theoretical study, okay? No issue. You can still write it like order of n. It is so it is plus minus 1, but no issue. It is still, this loop is still executing n times, huh? And then for j in range I plus 1, whatever the value of this I is, for first the I will be 0, and 0 plus 1 would be 1, and then size is again end. So it is reducing from the beginning, huh? This loop is reducing from the end, and this but only one time, but this loop is dropping element from the beginning. But in each iteration it is also maximum it is executing 4 times, huh? If the size is 5. So again it is 1 2 plus minus, no issue. It is again n times. It is again, and then there are two nested loops which are running n times. So then n multiplied by n. The rule is n multiplied by m multiplied by 1. Oh, rule that we have learned in the beginning, huh? Where there one loop was executing n time, other was m time. You asked the question at that time, huh? And then we multiplied n multiplied with m. Same. N multiplied by n. N multiplied by n, it will become power is 1 n square. 1 plus 1 n square. And this statement is taking what? Order of 1, order of 1. So due to these, where is that one? Sorry. Due to these nested loop, this is taking order of 1, this is taking order of 1, this is taking order of 1. But these, due to these two loops in this method, in this algorithm, it is order of n square. And how we can represent it in mathematically like that? It is like a parabola. Going here and going here. Order of n square, huh? This is graphical representation. Factorial complexity. How much is left? Okay. I made it red to stop here. Huh? He's happy now. He's happy, huh? Yeah. Factorial complexity. This is mathematics. Only up to this CLO 1, it is something more like a boring mathematics. But in the next CLOs, you will start some algorithms and then go on, and then you will feel more interest as compared to this CLO, okay? But then the complicated things will also come, okay? Factorial complexity. Factorial, you already know that. If I say 5 factorial, what it means? 5 multiplied by 4, multiplied by 3, multiplied by 2, multiplied by 1, and then you will get your answer, huh? And that would be the total number of options available. If some algorithm will have this factorial complexity, then it means that you will calculate factorial, and whatever the answer, that would be the total number of operations involved in that algorithm. Because running time is what? You have to find the total number of operations. And in the worst case, maximum number of operations. In the best case, minimum number of operations. Average case, average, real life, average, in the middle, huh? Average number of operations. This is what it means. So then factorial complexity, okay, now you have the understanding. When n factorial steps are performed on elements to solve a given problem by some algorithm, then if the steps performed by the algorithm to solve a problem is n factorial, where n is the size of the input, huh? Then the complexity of that algorithm, you can represent it as order of n square. And for that, here it is given, some algorithm is given here, permute for permutation, huh? And A is a string, L for left part, left, this L is the left letter of the, starting letter of the left, like your binary search, low and high. This is left, and right is the position of the last character in the string. And this is a string. L is equal to R, then print, and then you are joining. So this is constant, this is constant, this is constant, this is constant for I in range L plus R. So, okay, for L, initially, if L is 0 and this 0, 1, 2, this L is 0 and R is what? If I have given R is equal to 2 here and L is equal to 0 here, I have mentioned here. List is this. This is not the part of the algorithm, okay? This is part of the program, but not algorithm. Algorithm is, you can consider only this part, okay? But I have given it only for your understanding. List is this. Anyhow, so initially 0 and then 2 plus 1, it would be 3. And then this will loop will go on 0 to 3, also n times. Here we are doing swapping, order of n time, but we are calling permute this function recursive. With what? A is a string, L plus 1. Okay, L, if L is 0 previously, now it would be 1. You are dropping one letter. So initially, uh, you called this loop, you called this loop, which will run 0 to 2, 3 times, you can say, huh? Which one? And but now you are calling permute with 1 and 2, and now it is 1 and 3. So it will be, for example, 2 times, huh? Reducing. Okay. And then when it is come, it is L plus 1 is 2, and then you are calling again, and it is 1. Hmm? And when it is 2, when it is, sorry, when it is 1, okay, 1, and then 1 plus 1 is what? Yeah, I'm doing right or what? 0, and then 0 plus 1. Okay, yes. And then it will call with 1, 1 plus 1, 2, and then you are calling with 2 and 3, 2 and 3, maybe only 1. And sometime it will become 3 and 3. The base case will become true or like that. So it will be like that. This is what? And you are multiplying. How many times this loop is executed? 3, 2, multiply all that. So that behavior of factorial is there. Huh? So that's why the complexity of this algorithm is what? Complexity of this algorithm is order of n factorial. Hmm? Because you are on first call, it is calculating 3. On second call, it is recursive. So it is in the memory. I'm not calculating space complexity. I'm calculating running time. I'm calculating running time. It has a recursion and also a loop. So first iteration, first recursive call, okay, I'm going. So you can consider that this recursion is also behaving like a loop, outer loop here. And then you are calling that function. You are calling that function in the loop. So one iteration is recursion is also a kind of a iteration mechanism, but it is using stack. That stack, I will count it in space, but recursion is also has a mechanism of iteration. So it is calling 3 or 4 times. And when the first call, this loop is executing 3 times, which I have written here. Now the recursion, if consider recursion is a loop, now recursion is coming second time. First recursion is still in the memory, coming second time. How much? And then it is executing. How many times this loop is executing for that second call? 2 times. For next, it is 1 time. Due to that recursion, which is not finished yet, I am multiplying them, okay? Because that recursion is behaving like loops. And when you have block under a loop, we know that n multiplied by m multiplied by body of the block, or n multiplied by the body of the block. For single and nested loop, we know all the rules. And I am applying that rule here. That's why I am multiplying. That recursion is behaving like loop in for calculating running time. But this is now the block for it. And that block is taking how much time it is running? I know that 3 times first, then 2, then 1, then like that. So it has a property of factorial. So that's why the complexity for this algorithm is uh, factorial. And how it is doing? First, it is printing. When it is printing here, it is printing ABC, then ACB, changing these 2 letters, then BAC. So finding all possible disordering sequences. Huh? Exponential complexity. Exponential. There would be another one, I think. No. Okay, good. Exponential. Polynomial. It is not written here, but exponential. You have something and then you have exponent of something. Huh? That is called exponential complexity. Exponential complexity normally represented like that, some constant, and then you have some exponent, some variable as an exponent. Okay. This here n is the size of the input. Always n is the size of the input. Okay. And here you have the constant 2 raised power n. It can be 3 raised power n, it can be 4 raised power n, then 3, 4, 5, 6, all are constant. But power should be variable like n here. Okay. And if you have this situation, that in mathematics we call it exponential form. And if some algorithm will have this complexity, you can call it exponential complexity. When it will happen? When the number of operations multiplies by a constant factor with the increase in input. When the number of operation multiplies by a constant factor. For example, when you are right, when the size of the input is 1, okay, then 2 raised power 1. When the number of operation multiplied by constant factor, and when the size of the input is uh, doubled, initially 1 and then 2, if n is equal to 2. First I have taken n is equal to 1 element, then this is. If n is equal to 2, if I increase the size, then what? 2 raised power 2. Similarly, I increased, then 2, 3. If an algorithm has the size n is equal to 1, then the complexity is 2 raised power 1, 2. If the input has the size 2, then the complexity is 4. From 2, it is becoming double. Huh? And then if the size is 3, 2 multiplied by 3, 2 multiplied by 2, what it becomes? 8. 2 2s are 4 and 4 2s are 8. Huh? 8. So then previously it was, the size was 4 and now suddenly it is 8. Huh? And if you increase the size with the, increase the size of the input to 4, then it will become 16, from 8 to double. Now you understand the behavior. Huh? So when the number of operations multiplied by a constant factor with the increase in input, then you can call that such algorithm will have the complexity, exponential complexity. For example, if some algorithm is building some kind of a tree, first 1, 2 raised power 0 is 1, huh? One element. And if it is, and in the next step 2 raised power is 2, and then in the next step 2 raised power is 4, and then in the next step, sorry, it is like a tree, then in the next step it is like 8. Huh? So the algorithms which will go like this binary tree, something like that, they will have this complexity. Huh? They will have this complexity most probably. So example, order of 2 raised by power 1 below. Here Fibonacci we are calling due to 2 recursive calls. Okay, let's see. N is the size, and here you are checking n less than or equal to 1 when this condition will true, and then you are returning n. Else you are returning Fibonacci. You are calling this function again by reducing this n with -1, and Fibonacci again by reducing it with n minus 2. If n is 5, the first call is 5, and then the 5 you have 4 here, one call with 4, other call with 3. Huh? And then this 4 will go again, and it will call further 2. 4 is 3 and maybe 2. Huh? And then this 3 call will go, and it will have 2 and 1. Huh? And this will further go 2 and 1. This will further go, sorry, 1, slide is finished here, 1, 1 and 0. And here it will be checked 1 less than equal to 1, equal, yes, equal, and then return. And 0 less than, yes, return. Then this will return and first pushing and then popping due to recursive. Huh? Stack is used, but I'm not calculating space complexity. But recursion is also behaving like iteration in loops. So here you are calling two recursive calls. So due to these two recursive calls, you have two here. And this 5, 4, 3, 2, 1. Look at this behavior. 5, 4, 3, 2, 1. In each tree, you will see this 5, 3, 2, 1. On this side, and also you will see some mechanism n times here on this side. So due to that, 2 raised power n. Okay. Due to that, 2 raised power n. Uh, and this is the graphical representation, how factorial will go like that. And I hope that now I'm stopping here. Any question up to this point? He's saying, Khalli Walli. He's saying, Khalli Walli, leave us. Leave us. We are full, huh? Okay.